something as ck into e power jk omega naught t. F of x is equal to summation k equal to minus infinity plus infinity ck e to the power jk omega naught t. So now, if you truncate that right hand side to only n terms, then you get an approximation, and that you denote as f subscript n of x. So fn of x is an approximation of the function f of x. So this function fn of x, if you plot it, it will wander around the function f of x. That means it will go above and go down the function f of x. It will not lie on the function f of x. That is, it is not equal to the function f of x at all x between an interval a to b. Suppose you have an interval a to b and you are looking at the function f of x. So x is going from a to b and you are looking at a chunk of f of x in that interval. Then fn of x will be going up and down f of x. It will not lie on top of f of x. So, but the idea of uniform convergence is that this fn of x will be lying between two bounds. One is fx plus epsilon and fx minus epsilon. So there will be two bounds or two curves above and below f of x function, between which the fn of x function will lie. So this idea is called uniform convergence. So you can prove that if a function is absolutely summable, then it exhibits uniform convergence.
Excuse me, sir.
Yes.
Some students are waiting to be let in.
Only one guy.
It might have timed out, sir. 2-3 students were waiting. Let's check this.
Okay, so I think you have understood the idea of uniform convergence. So this absolute summability criteria is a very tight criteria. It may not be valid for many functions. So the DTFT exists for a broader class of signals beyond those that are absolutely summable. So some discrete signals do not satisfy this above equation, this absolute summable equation, that is equation 6.7, such as then what to do? How would you think about the discrete time Fourier transform? So in such cases, DTFT may exist in only a generalized sense or with weaker than uniform convergence. So one idea is that signal with finite energy. The signal with finite energy characterized like so this is less than equal to this term, okay, and which is less than infinity. So for such signals like sinusoids or sinc functions, they have finite energy, and therefore they are said to be like signals which don't show uniform convergence, but they exhibit what is called convergence in the mean. So let us see what is convergence in the mean. So here you have x of omega, which is the DTFT, and here you have the summation going from minus n to plus n, where n is less than infinity. Okay, and you are trying to find out the difference between x of omega and this term, and this term is supposed to be continuous thing, therefore integral, because the dtft is a continuous spectrum, so integral comes here, and you are taking the square of this argument. Okay. Just hold on, I need to take a call. Okay, can you hear me again? Yeah, am I audible?
Yes, sir.
Okay. So we are talking about finite energy signals. So we are talking about convergence in the mean. So this was the idea of convergence in the mean. So this is weaker than uniform convergence. So DTFT of sink of n exists, although it converges in the mean and not uniformly. So this is something that we should understand. Now we are talking about finite energy signals. Now there can be some signals which are not having finite energy. They are a power signal, they don't have finite energy. Their energy content is infinite. So to produce a DTFT of a sinusoid, you need to introduce what is called a generalized function. That is delta of omega. Now delta of omega, omega is continuous. Okay, frequency, continuous frequency. Delta of omega is not Kronecker delta, it is Dirac delta. So Dirac delta is a generalized function. That means at omega equal to 0, it is undefined, although its area is unity. So this you have to keep in mind. So if generalized functions such as Dirac delta, then we can even find the DTFT of some signals that violate both 6.7 and 6.8. That means both these two conditions are violated. Neither the signal is absolutely summable, nor the signal has finite energy. So a sinusoid is such an example. So bounded amplitude power signals, for example, are neither finite energy nor absolutely summable, yet they have DTFTs. Okay. So the DTFT of x of n is equal to 1 is this. And the DTFT of e to the power j omega naught n is this. So this is a complex sinusoid, and this is a constant signal, a DC signal. So a DC signal, constant with 1 or maybe k, is infinite energy signal, and so you can still have its DTFT. So this is not a finite energy signal. Neither it is an absolute summable signal. But still you can have its DTFT by using generalized functions or Dirac delta functions. So there are still some more functions for whom the DTFT simply does not converge. So I had talked about a to the power n un, or here he has written it as gamma to the power n u of n. So this is an exponentially growing signal where gamma mod greater than 1. Okay. So gamma mod, that is the modulus of this uh, complex, or rather the exponential is greater than 1. So it will violate both absolute summability as well as finite energy. That means it has infinite energy and it is not absolutely summable. So it is not having a DTFT even in a generalized sense. So even using generalized functions like Dirac delta of omega, you cannot produce a DTFT. So the DTFT does not exist for such signals. So how to analyze such kind of signals? So we will look at another kind of transform, which is the Z transform. So that will be covered in the next chapter. So using Z transform, we can analyze growing exponential also. So we can take the Z transform of such a kind of signal and then try to see what happens. So still some people are coming in. Mm, yeah, continuously people are going out and coming in. That's the problem. They are losing internet and then they are coming back again. Anyway, so let us continue. So the DT of a single sample, that is Kronecker delta. So xn is equal to 1, n equal to 0, and elsewhere it is 0. That is equal to delta of n. This is different from the Dirac delta. So what is uh, the DTFT? It is going to be this unity all over the frequency. You can prove it like this. This turns out to be 1. DTFT of right-sided exponential. So this is the problem, and therefore we put the condition mod of A is less than 1. So we can only find out the DTFT of a decaying exponential. We cannot find the DTFT of a growing exponential. So if you find out the DTFT, you can use the geometric series. So it is geometric infinite series 0 to infinity. So this is the geometric ratio. So you can find out this formula. So this formula is a closed form expression only when mod of A is less than 1. If mod of A is greater than 1, then this formula does not converge. So you will get infinity as answer. Okay, is this clear? So now let us analyze this particular formula and let us see like what we can think about its magnitude and phase spectrum. So if you look at this formula, you can expand this out by taking e power minus j omega as cos of omega plus j sine of omega. So you multiply minus a into cos of omega minus j a into sine of omega. So if you have to take the modulus, then you have to take the square root and square the real part and the imaginary part. Just hold on. Okay, so we were looking at this magnitude plot and the phase spectrum. So if you plot the magnitude plot, you will get something like this. This is an even function, and the phase spectrum will turn out to be an odd function. So here the solid line denotes the spectrum for a equal to some value, so typically something like 0.9, and the dotted one shows the value or the spectrum for a equal to 0.5. So the phase spectrum turns out to be odd, whereas the magnitude spectrum turns out to be an even function. So this is something like an exercise, like how would you try to find out the inverse DTFT? So, so you can use this formula and you can find out that this is 0.3 to the power n u of n. Okay, so now let us come to the sinc function. The sinc function and the rectangular function, the rect function, those are a DTFT pair. So all this you would have studied in your signals and systems course, but just for the sake of revision. So if you see here, the sinc function is not an absolutely summable function. So if you take directly the DTFT of the sinc function, then it will not converge. Okay, it will tend to infinity. But using the property that there is a DTFT transform pair between this rect function and this, we can say that the DTFT of a sinc function is equal to the rect function. So the rect function has the cutoff frequency as omega b. And if you see here, this is actually omega b by pi sinc of uh, omega b m. Okay. So uh, this turns out to be a sinc function. This you can write it as a sinc function by using omega b by pi into sinc of omega b m. So omega b is here, and it is the cutoff frequency. So this is something that you should note. So this is actually the ideal low pass filter or the brick wall filter. This is supposed to be non-realizable because in the amplitude spectrum it is a rect function, and if you take its inverse Fourier transform, so suppose this function was the impulse response or the frequency spectrum, or rather the frequency response of an LTI system, then the inverse DTFT would be a sinc function, and that will be the impulse response of that LTI system. And that impulse response will have finite terms on the negative x-axis or the negative axis, and therefore it will be non-realizable. So it is a non-causal system. So if you have an ideal low-pass filter, it is a non-causal system and it is non-realizable. So the DTFT of rectangular pulse. So here we start thinking of slowly combining different formulas for DTFT and trying to find out how to find the DTFT of the sequence where you have combinations of discrete sequences. To start that, let us look at the rectangular sequence of length L. So n goes from 0 to L minus 1, and there it is 1, otherwise it is 0. So you will be summing from 0 to L minus 1 into e power minus j omega n. So that turns out to be this formula, 1 minus a to the power n by 1 minus a. So you use that formula for a finite geometric series, and you can simplify this formula in this form, where this part is called the Dirichlet function. Okay. Sine L omega by 2 divided by sine omega by 2 is called the Dirichlet function. So a pulse of width n naught has this particular form of DTFT. Is it clear, everyone? Fine, shall I move it? Please let me know. Okay.
Yes, sir.
So this is some summary of DTFT pairs that we have studied till now. So if it was delta of n, then it will be 1. Now it is delta of n minus nd, which is shifted Kronecker delta. So you get e power minus j omega nd as its DTFT. Now this is the decaying exponential, right-sided exponential. It has this closed form expression. And for the sinc function in the time domain, you have the rect function or band limited rect function. So the sinc function is band limited. And if you have pulse of unit magnitude, which is from 0 to L minus 1, then the L point pulse, then you get this particular form of the DTFT. So now, how can I combine different sequences and try to find its DTFT? We'll come to that, but just before that, some properties. So again, the conjugate symmetry property. So here again, this will exhibit the real signals. They have a DTFT which will have even spectrum or even magnitude spectrum and an odd phase spectrum. So how to show that? So for a real signal, x of n is equal to x star of n. Okay. So this is in time domain n. For real signal. So if you take the DTFT of both sides, then for the conjugate, you have this particular DTFT. And we have seen this in the previous slides. So then you can write, you can show also that how this comes. So you can take y of n as x star of n and find out y of e power j omega. You can directly do this. So if you do this manipulation, then it turns out to be x star e power minus j omega. Okay. So in the notation of Lati, it will be x star of minus capital omega. Okay. So this slide is pretty important because most of the times we use real signals, so we should understand about its DTFT. So I think you have all written this down.
Yes, sir.
Okay. So the magnitude and angle plot for this particular case, and this is a real signal. a to the power n u of n. So how does the magnitude and the angle plot look like, which I've already shown you. So it will be like this. So the magnitude spectrum is even and the phase spectrum is odd. So for varying values of A, you will get different plots. The solid plot is for A equal to 0.9 and this is for 0.5. This is for a real signal. A to the power n, u of n is a real signal. So decaying exponential. Some properties of DTFT, linearity, time delay, so frequency shift. We have already seen this. The frequency shift is interesting. It is multiplied by a sinusoid, so that is also called the modulation property. So this omega c is the carrier frequency actually in communication systems. So the carrier is a high frequency, and omega, the content of x of n is generally baseband. So x of omega is shifted to x of omega minus omega c. So this is the modulation property. And the time delay in the time domain results in only a phase shift. It doesn't affect the magnitude spectrum. So this is very trivial. These are just properties, proofs. So how to find DTFT of combination of sequences? So suppose you have y of n as equal to 1 for n to n0 minus 1 and as minus 1 from n0 to 2n0 minus 1. Okay. So it is something like a pulse which is both positive and negative. So positive for some samples and negative for some samples. So we have seen the DTFT of the first part. We can use that in the second part and then we can get the combined signals DTFT. So yn can be written as x of n minus x of n minus n naught. So what is x of n here? So x of n is supposed to be this. So we already know its DTFT. And so we have seen that for this particular form, the DTFT comes out like this. So we can write the DTFT of y of n by using another property of DTFT, which is the time delay property. So using properties to find the DTFT of sequences. So many times you can write realistic sequences as a combination of these typical sequences. Okay, is this fine? So y DTFT of the yn signal y of omega can be obtained by writing as x of omega or x of e power j omega minus e power minus j omega n naught into x of e to the power j omega. So x of e to the power j omega is given like this into e to the power minus j omega n naught. You will have extra term here. So y of n turns out to be this. Y of e to the power j omega is equal to x e to the power j omega minus e to the power minus j omega n naught x of e to the power j omega. So you can simplify this. You can take x to e to the power j omega common and you can simplify this. So it turns out to be this. Okay, this example is clear.
Yes, sir.
So like this, you can have many examples. So in the Latti's book, I think in the data communication book, analog and digital communication, there is a typical example of a truncated sinusoid, a sinusoid which is cut from one place to another place. So it is a sinusoid pulse. So there in that book, he had shown the continuous time Fourier transform of such a signal. So you can take a look at that kind of example. So maybe the sinusoid was a discrete sinusoid, then how would you find DTFT? So just like you can have various questions for continuous time Fourier transform, similar analogous questions you can have for DTFT. So this frequency shift property is the proof. So this is our fundamental pair, DTFT pair. How can I use this to find some DTFT of another sequence? So let us see. Sync times sinusoid. So we are supposed to find the DTFT of a sync multiplied with a sinusoid. So this is our sync function. This is multiplied by sinusoid. So what is its DTFT? That is the question. Or you can have something like this. So this is a cosine function, and if we want to understand what is the DTFT of this guy. So if you multiply by cosine, then you are getting both shifting up and down, because you are having the cosine as a summation of these two terms. So these two complex exponentials, they will shift the frequency up and down. So you can try to do that as an exercise. So this is the idea of the eigenfunction. So this equation is something extra. We had up to this. This is the extra equation. So if you multiply, or if you are convolving the x of n, then you are multiplying h of e to the power j omega naught into x of e to the power j omega naught. So this is the idea. Then ideal low pass filter. So it is 1 in the pass band, 0 in the stop band, and this particular guy is the cutoff frequency, omega c naught. So we know that the DTFT pair is a sync function. So you have to find the input output when the input is a sinusoid. The sinusoid is with this frequency. So what will be the output? So what is this? So it will preserve this sinusoid. So this is a sinusoid whose spectrum will come here like this. So it will preserve this sinusoid. So you will multiply this spectrum with this spectrum. Okay, if you see the previous expression, this is the guy. Of e to the power j omega naught into x of e to the power j omega. Okay, so you're multiplying, and you'll be preserving this. So multiply the spectrum of the input times the DTFT of the filter to get this. This is the output. Why? So your signal is preserved because the spectrum is lying inside the passband. If the spectrum would be lying outside the passband, then it would get destroyed. It will not come out at the output. That output will be zero. So if you see in the time domain, it is such a complicated operation. So it is a sinc function convolved with a cosine. But in the frequency domain, it comes out very simple. So this is the advantage of using Fourier transforms. Fine. Is this idea clear? So an ideal high-pass filter. So the impulse response of an ideal high-pass filter is actually delta of n minus this guy, low-pass filter. The low-pass filter has the impulse response as a sinc function. If you subtract delta of n, from delta of n, if you subtract out that sinc function, then this is the formula for the impulse response in the time domain. In the frequency domain, it is like this. So this frequency domain spectrum looks like this. So this is the ideal high-pass filter. 1 in the pass band, 0 in the stop band. The band pass filter has 2 stop bands. And the band reject filter will have 1 stop band and 2 pass bands. And that is 1 minus the band pass filter. So how to make an ideal band pass filter from a low pass filter? So again, you can use these ideas. Frequency shifting 1 up and down by multiplying a cosine term, and then you can obtain a band pass filter from a low pass filter. So you can shift a low pass filter towards the right and you can shift it towards the left, then you can get a band pass filter. So to do that, you have to multiply a cosine term with the impulse response of the low pass filter. Okay, so I think I'm just stopping with this today. We'll continue with a little bit more examples and then we'll move into Z transforms. Hopefully we will do Z transforms in the next week. So I'm not very sure that on Friday I can take the class because I have vaccination on Friday, second dose. So for my family and one of my PhD students. So I have to take them. And so Friday class will be off. So today I will stop here. And I don't think I'm going to take the class on Friday. So I'll inform you the status on Friday. So we have a class from 10 o'clock on Friday, so I don't think I can take it because the vaccination is from 10:30. So I would like to go to the BC Roy Hospital at that time. So class will not be there on Friday. Okay, so we'll meet next week. And next week, most probably, we are starting Z transforms.
Sir, we don't have a class on Friday, sir.
Thursday, sir. Actually.
No, we don't have a class on Friday because I have a vaccination on Friday.
I mean, we don't have it in schedule. We have it in Thursday.
Actually, it is on Thursday, sir. Thursday, sir.
It is on Thursday. Okay. Oh, then it has kind of slipped my mind. Okay. I think third is Friday, right? What is third? Today is 31st, no?
Friday.
Yeah, so third is Friday. Then possibly Thursday class I will take. Okay. Thursday is second, no?
Yes, sir.
I'll see. Like I'll inform you. There are so many things in this week, so like I'm not very sure about the next class. Okay, fine. Today it is enough, and I think next class onwards we will start Z transforms. So all of you should be looking at the problems in Oppenheim and Schaeffer. So there are some basic problems and there are some advanced problems. You can start off the basic problems. The answers are also given in the book at the back. So you can start off with the basic problems. Chapter number 2. After the introduction chapter, the discrete time systems chapter that has both DTFT as well as LTI systems. So you can start working out those problems. Start with the basic problems. And, you can also try the advanced problems, those who are more confident. Okay. Fine. So thank you. I'm ending the class now. Okay.
Thank you, sir.